Okay, so here is our infrared lab, and the idea here is that we're going to build a circuit that exists on two breadboards, and there's going to be an emitter of LED light, or you can think about it as an illuminator or a transmitter, and then we're going to have a detector of infrared light over on this side. And so that's the detector, it's a phototransistor, or it's the receiver. The idea is transmit infrared light here that will be invisible to us, and then receive it over here, and then we'll use a voltmeter as an indicator that we're actually picking up that light that comes from here and is measured here. The infrared devices that we're using are an infrared LED. Now we've already experimented with red. You may have experimented with the green. We looked at the RGB LED. This is a single LED that just emits light in the infrared part of the spectrum. And it looks like it's a little smaller than the other LEDs we have. This one is actually 3 millimeters in height, whereas the other one is 5 millimeters in height. It has two leads. Like other LEDs, not the RGB, but the red and green, like those, the longer lead is the anode, which is where we put the positive polarity from our power supply, and the shorter lead is the cathode. Over on this side, instead of using an LED, we're using what's called a phototransistor. This is a two-terminal device. Now, we haven't talked about transistors in class yet. We'll be talking about that next week. But all you have to know here is that this is a device that will take incident light energy that shines upon what's called its base, and then it turns that light into a current that emerges through the emitter. So what's going to happen is when we have the transmitted light from here that gets picked up over here because these are in proximity to each other, then the photons of infrared light that are incident on this get converted to a current. That current will flow down through what's called the emitter terminal. The current through that emitter multiplied by that resistance, and it's a fairly large resistor, will give us a voltage. And what we'll then be doing is using our DC multimeter, our meter set up to measure DC voltage, and we'll just be measuring the voltage across that resistor. And we're going to be using a common battery pack to power both of these. So I've got some indications here where we're just extending the voltage rails, both the 6 volt and the power rail. We're extending that from this board to this board using some fairly long wires that you have in your kit. And then what we want to do is see how far apart we can put these together, move them apart, and see if we can still detect the light beam that's sent over from the illuminator to the detector. And then we'll do things like put our hand in the way, put other things in the way, and maybe experiment with blocking that beam. Okay. One particularly tricky thing about this experiment is that the IR LED and the phototransistor are both two-terminal devices, and to your eye, you cannot tell them apart. Now, I've taken them and I've bent the leads, but in your kit, they'll just have straight leads. And the reason why I've bent them is that I want to be able to aim them sort of toward each other. So I'll have one on one end of a circuit board aiming toward the other one at the other end of the circuit board. And that way, the light that's transmitted by one is able to be directly picked up by the other one. So that's why I put those bends in there. But we have to figure out which is which. I mean, if you just look at them, you can tell that each one has one lead longer than the other, right? A little bit longer than the other. Let's go back here, right? So the one lead that's longer than the other is either going to be, if it's the IR illuminator, the LED, then the longer lead is the anode, the shorter lead is the cathode. But for the phototransistor, the long lead is what's called the emitter, which I've indicated with the E here, and the shorter lead is the collector. I'm using capital C here, and that's what's shown here. So how do we determine these apart? Well, fortunately, your multimeter has a function on it that can actually test diodes, and so it's shown down here. It's a symbol that looks like a diode. So I'm gonna turn that all the way around there, and what I'm doing is first I'm just going to grab a common red LED. So I'll show you how this works. So I've got a red LED, and what I'm going to do is connect the meter to it in the direction of forward bias. So that is the red lead on the anode and the black lead on the cathode. And what you can see is that the LED is glowing, and it has a voltage drop of 1124. That's millivolts. So it's 1.1 millivolt is what's being dropped. So this is telling us that this LED is working. It's glowing, and it also has a voltage drop when we energize it with the meter. If we went in the other direction, right here I've reversed them, then the meter just shows a 1, which is an overage or an overscale. In other words, it's not getting any detectable voltage drop. So that would mean that the LED is open circuited. So this is what we're going to find we're able to do to locate which one of these little devices is our LED and which one is the phototransistor. So I'm going to start out. I'm going to find out which lead is longer. So I have this lead is longer, and I'm going to connect that to the red lead. Now I may need to use the alligator clips here if I run out of hands, but it looks like I'm okay. Okay, so here I'm getting a voltage drop. It happens to be 0.663. Now don't confuse that with V sub F that we use for design. All we want to know is, are we getting a voltage drop? So here we're clearly getting a voltage drop of 0.66 volts. And if I went in the other direction, I get an overage, right? So that tells us that this one is the LED, probably. But let's also take this other one. We now think that we presume that this is our phototransistor. I'm going to go and hook that one up. Okay. Now what did I get there? I'm reading 0. I'm reading an overage. Okay. So that indicates this one is not our LED. Yeah, as it just sits there, I get an overage. So this is our phototransistor. I do want to show you something about this. So I'm going to need some alligator clips, and I'm going to just continue that test. This one, this is our phototransistor, and we know that because it didn't indicate a forward voltage drop with our meter. But I am going to show you an experiment that we can do. Okay, I've run out of hands for this, so that's why I'm using my clip leads. Okay, so we're just reading an overage, meaning it's not reading a voltage drop. Since it's a phototransistor, what it can do is it can convert incident light into a current. So I've got a bright flashlight, and I'm going to shine that flashlight on there. Now the flashlight has some infrared energy in its beam. So when I shine that on there, I'm actually pouring a lot of infrared energy in there. That's creating a current, and that is giving us a reading on the meter. And that's indicating it's the voltage drop that's being measured as this phototransistor is converting that incident infrared energy into a current, and then the meter is interpreting that as a voltage. So you know this one's the phototransistor because I take it away, and it's so obviously light sensitive. So what we've been able to do is discern which one of these is the phototransistor and which one is the LED. So now let's not confuse them. Let's put the phototransistor on the right, and we'll keep the LED on the left. Okay, so now let's start to assemble this circuit. And what I'm doing here is I'm going to put the LED at the far end of one board, and then I'm going to put the phototransistor at the near end of the other board. So that way I can have them, sort of, this one is transmitting, the one on the left transmitting, the one on the right is receiving. They'll be on the ends of the board, and what I'm going to do is move the boards apart. Okay. All right, I've bent this one. What I want is in my circuit, I want the anode, which is the long lead, is going to get connected through a resistor up to our positive voltage rail. So let's go and build this one. So there's the LED, there's the anode here, and the cathode here. Okay, and what I need is a 200 ohm resistor. Now, the 200 ohms comes about from the analysis that we've done, and you can read you should read the accompanying analysis document. When we use 200 ohm resistance, we're not running the infrared LED at the maximum possible current and hence the maximum possible power, because we want to be conservative. We only have one of these in the kits. We want it to last. We don't want to damage it. So we're using more resistance than we need to use. We're not running it at the maximum current. We're trying to keep it at a safe level. Okay, so now I need to go down to the okay, I can see already a potential problem here. I've got the breadboard turned around, where I've got the very top rail is actually labeled minus, and I prefer always to have the top rail be the very top rail be the positive rail, and I find I make fewer mistakes that way. So I'm going to take everything apart, turn this around, and then rebuild it. I've just found over the years, one makes fewer mistakes if I always hold my breadboards in landscape, and I have the very top rail as the positive voltage rail. Okay, we'll put those resistors back in. Okay, so there's our transmitter or our infrared illuminator circuit. We just need to connect the battery to it and that'll be going. But now let's also build this receiver circuit. So this is a complicated looking device, this phototransistor. It really just has two terminals. It has the collector and the emitter. Right? And the emitter is the long lead. The collector is the short lead. So here we have, you can see we have the long lead and the short lead. And I've bent this so that I can put it in the breadboard. Emitter here, we're going to connect that through a resistor to ground. And then we have the collector, which we're going to tie to the positive rail. And you can see these are bent so that they're aiming toward each other. Okay, what else do I need? I need to put in this resistor here. Oh, and I'm doing it again, aren't I? I'm building it turned around. There. This is my preferred way of orienting these. So the very top rail is the positive voltage supply, and you'll see in the next step why that's so important. Okay, we'll put this back on. We put our resistor on. Okay, I need to wire up this between the collector and the positive voltage rail. Okay, so the next thing we have to do now with this is apply power, and we have to connect the voltage rails between the boards, and then we'll hook up our meter. So I've gotten a couple of the long wires from the kit. There's a black one and the red one. Your kit has mostly short wires, but then there are a couple of these longer wires, and we're going to use those to extend the spacing between the boards. So here what I'm doing is I'm directly connecting the positive and the negative rails of the boards. Let me just step out so you can see that. Okay, and I've connected those, and using those long wires, I can bring this system apart like this. And so what we want to do is experiment. As we're creating a light beam, we want to experiment with blocking that beam and moving the boards apart. Okay, we need to attach the battery over here, and then we also need to connect the meter over on this side. And so we're going to be using the meter as a way of measuring the voltage that's developed across this resistor here. And so to do that, what I'm going to do is I'm just going to put another piece of wire right in there. Okay, that's going to be a wire right at this node where the emitter and this emitter resistor are connected together. So you'll see it's a wire that's right here. All right, and that's going to be the red terminal for the multimeter. And so I'm going to go back and get my alligator clips to do this so that I can do this hands-free. I'm going to put the red one, and then the black one to connect that black probe. Well, I'm going to get another little piece of wire, put that in my negative rail, connect the alligator clip. Okay. All right, so we're ready to apply the power. I'll take that away. Maybe I'll step this back so that you can see the whole thing. Okay, let's just run through what we've got. We've got our illuminator board, and we're going to apply 6 volts from the plus rail to the minus rail. And you can see that the plus rail, of course, runs all the way along the left board, and then we've extended it to the right board with that long red wire. Likewise, we've connected the ground rails. So I have this illuminator circuit where I have the diode the anode is connected to plus 6 volts via 200 ohms, and then the cathode is grounded. When I power this up, this will emit infrared light that we won't be able to see, but it'll be picked up by this phototransistor. There'll be a small current that's flowing through the emitter. Then it'll flow through the 10K resistor where it'll get turned into a voltage, because current through that resistor will create a voltage drop, which will then measure on the meter, which is configured on the 20 volt DC scale. So all that remains is to hook up the battery. Okay, and what we see is a voltage of 0.64. It's a significantly smaller voltage than I would have imagined. I expect to see a voltage around 5 volts. I pull these apart, block that light. Okay, the light's not actually being blocked. So here, let me show you what's happening here. Let me go ahead and disconnect the LED for a minute. And you see that this doesn't change. I designed this so I expect several volts at this point, but I'm not reading it. I'm reading 0.64. What's it doing? It's actually measuring the infrared light coming from the ceiling. If I know this is off because I'm holding this LED in my hand. So I'm trying to debug what's happening. If I cover this up, that drops down. That's just interference from the light in the room that's shining down. And if I cover this up to try to block some of that room IR energy, you can see that voltage drops. Okay, when I go back and rebuild this, I'm going to show you the problem that I made in my wiring. I'm going to zoom in. And if you look right in here, you'll see that these two resistors are in different columns. So when I built this, I inadvertently put this terminal of this resistor in the wrong column. So I have to move it over. Okay, so now this thing is on, and if I step back, you can see I've got a nice strong voltage, right? In fact, the battery voltage here is 6 volts, and I'm reading 5.75. So I'm almost reading sort of the maximum possible value from that receiver. So now let me separate these apart. Maybe I'll put the meter kind of right here. A little messy with the wiring. So you can see that voltage reading is going down. All right, it's 5.26. Let me block the beam. Okay, that's the effect of my hand. I'm breaking the light beam. So what I've got here is an invisible light beam. You think about it as a tripwire. Okay. If we had a separate battery pack, we could completely separate these boards. One powered by its battery pack, another one powered by its other battery pack. We wouldn't have these wires at all. But what we can do is, let's suppose that I'm walking across here and I break that beam. Right? We detect that break as a decrease in the voltage here. And we could use this as an alarm circuit, as a tripwire circuit, if we wanted some indication something has broken that beam. How we would process that signal and actually turn this change in voltage into some kind of an alarm or indicator, we're going to get to that in a couple weeks in the class when we introduce operational amplifiers. But you can see that what we've built a circuit now that has a transmitter and a receiver, or an illuminator and a detector, and we're generating infrared light that we can't see, but it is being picked up by the infrared photo transistor and being converted to a voltage, and then we're measuring that here. And we can aim these things. We may even be able to do something like hold them up like this and see if we can detect the presence of my hand. Now that's too messy an experiment to be able to do without planning. Maybe I'll try to do it this way. What I wanted to do is see if we can actually detect that light is being transmitted between one and the other by reflecting off of an object. So here, if I put my hand there, there I'm getting a little of the effect that I wanted, right? Take away my hand, and I've got that lower voltage. Introduce my hand, and at a point, you can see that the voltage is actually increasing. So what's happening is that some of that infrared light is bouncing off of my hand and then back and being detected by the receiver. The change that we see over here is relatively small. I mean, we were really going from, here we're at 1.41 volts, take my hand away, 0.84 volts. It's a relatively small change. But there are all kinds of processing tricks that we can do where we put in electronics and things down here that can just detect the difference between that 0.9 volts and then this 1.32. That would allow me to detect the presence of an obstacle. Okay, so that ends that lab.